What is time? We feel it passing every second of every day. It seems so constant, so familiar. Yet, ask scientists what it truly is, and you find it's one of the most slippery and debated concepts in all of physics. So let's explore the weirdness of time. Think of time like another dimension, alongside the three dimensions of space: up, down, left, right, forward, back. Einstein showed us that space and time are actually woven together into a single fabric called spacetime. Imagine it like a giant stretchy sheet that makes up the universe. Now, one of the most obvious things about time is that it seems to flow in one direction, right? We move from yesterday through today towards tomorrow. Cups fall and break, they don't leap back onto the table whole. Why? This is the arrow of time. The best explanation we have involves something called entropy, which is basically a measure of messiness or disorder. Think about your room. It's much easier for it to get messy than for it to spontaneously become tidy, right? There are just way more ways for things to be disordered than ordered. The universe as a whole seems to follow this rule. Things tend to get messier over time. This natural trend towards increasing messiness is what scientists believe gives time its forward direction. The weird part? The fundamental rules governing tiny particles don't seem to care which way time flows, making the arrow we experience even more puzzling. It seems to emerge from probability and how things started. And how things started is perhaps the biggest puzzle of all regarding time's arrow. If things naturally get messier, then the universe must have started in an incredibly tidy, ordered state billions of years ago, what we call a state of very low entropy. Just how unlikely was this initial tidiness? Think about how unlikely it is to see a scrambled egg unscramble itself, or spilled milk flow back into the glass. These things seem impossible because the messy state is so much more probable. Well, the initial ordered state of the entire universe was, according to our understanding, vastly more improbable than unscrambling an egg. The odds against the universe starting out so perfectly orderly, allowing for stars, planets, and eventually us, are astronomical. Why the universe began in such a special, unlikely state is one of the biggest unanswered questions, and it's directly linked to why we experience time flowing forwards. Now, let's talk about time being flexible, as Einstein discovered. He realized that time isn't fixed. It changes depending on how fast you're moving. Imagine you're always moving through the combined fabric of space-time at a constant total speed, the speed of light. If you're standing still in space, all of that motion is through the time dimension. Your clock ticks normally, let's say 1 second per second. But if you start moving very fast through space, you have to borrow some of that fixed total motion from the time dimension. This means your movement through time slows down. So the faster you travel through space, the slower your clock ticks compared to someone standing still. Whose time actually changes? This is the beauty of relativity. It's relative. If you're zooming past Earth in a super fast spaceship, your clock feels perfectly normal to you. But you would look back at Earth and see their clocks ticking faster than yours. Meanwhile, people on Earth looking at you would see your clock ticking slower than theirs. Each observer sees the other's time moving differently due to the relative motion. Does this mess up cause and effect across the universe? Surprisingly, no. While observers might disagree on how much time passed between two events, the structure of spacetime ensures they will always agree on the order of events that are causally linked, like sending a signal and receiving it, as long as nothing travels faster than light through space. Relativity preserves the sequence of cause and effect. But what about light itself? What's the perspective of a photon, a particle of light traveling at the speed limit? According to relativity, something truly bizarre happens. Time stops. For a photon, the journey from a distant star to your eye, which might take billions of years from our perspective, happens instantaneously from its point of view. Concepts like speed or duration become meaningless if no time elapses. This immediately raises deep questions. If photons don't experience time, does that mean they also don't experience cause and effect? And if time stops only for them, while it continues for the rest of the universe, how does that work? What about when we travel incredibly fast, close to light speed? We see the universe fast forward. If we could hit light speed, would all those fast-forwarded events suddenly happen at once? The stopping of time is specific to the photon itself, along its unique path through space-time at the speed of light. For the rest of us, for planets, stars, galaxies, and any observer moving slower than light, time flows onward. Our clocks tick, events unfold, and the universe ages. The photon's timeless journey is an extreme case of Einstein's relativity, but it doesn't stop the clock for everything else. Think of it as the photon having a unique, personal timeline of zero length for its travel, while everyone else has their own, longer timelines. Do they experience causality in the way we do, observing a cause, then waiting a period, then observing an effect? No, because they don't experience that waiting period, or any period at all during their travel. An event causes a photon to be emitted, like an electron in an atom losing energy. That photon then travels. Its absorption by another atom or detector causes another event, like an electron gaining energy, or a signal in a detector. The critical thing is that the sequence of these events, emission before absorption, is maintained for all observers in the universe who do experience time. The photon is the link in that causal chain. It connects a cause at one point in spacetime to an effect at another. So while it doesn't experience the temporal journey between those two events, it is the very thing that makes that causal connection possible across space. Causality isn't violated by the photon. The photon is a key player in the universe's causal machinery. Say 99.999% the speed of light, time on your ship would slow down dramatically compared to the outside universe. Looking out, you would see the universe's events unfold in extreme fast forward. Stars would appear to be born, live, and die rapidly. Entire civilizations could rise and fall in what feels like a short time for you. The sequence of causes and their effects in the external universe would still be there, just playing out at an incredibly accelerated rate from your viewpoint. Now, what happens as you try to bridge the gap from this super fast-forward view to the photon's all-at-once or zero-time journey? This transition is best understood as a mathematical limit. As your speed gets ever closer to the speed of light, the time dilation factor, how much slower your time runs compared to an outside observer, gets ever larger, approaching infinity. This means the duration of external events, as perceived by you, gets squashed ever shorter. An eon in the universe might pass in a microsecond of your time, then a nanosecond, and so on, as you approach the speed of light. For a photon, which is at the speed of light, this squashing of external time along its path becomes complete. From its perspective, the emission, start point, and absorption, end point, are in its own proper time coincident. There is no during for it. Imagine the universe's history as a very, very long film. If you're moving near light speed, you're watching it on extreme fast forward. If you were the photon, it's like you see the first frame, your creation, and the last frame, your absorption, with absolutely no film reel passing in between from your point of view. The film still exists and played out for everyone else, but your particular seat in the cosmic cinema allowed you to skip all the intervening frames in terms of your own time. So the effects of relativity regarding time are indeed local to the observer or particle. Your experience of time depends on your motion and gravity. For photons, this locality results in a timeless journey. For the rest of the universe, time and its associated chain of cause and effect march onward, with photons acting as vital, albeit timeless from their own perspective, messengers within that grand cosmic story. So time, it's a dimension, linked with space. It flows forwards, likely driven by the universe's journey from an incredibly unlikely ordered beginning towards increasing messiness. It bends and stretches with speed and gravity. And for light itself, it ceases to exist altogether. It's woven into the fabric of reality, yet it remains one of the most profound mysteries we are still trying to fully understand. Let me know your thoughts in the comments below. Subscribe for more explorations into science and philosophy. Thanks for watching, and see you in the next one.